Hello, my name is Byeonggon Kang and I'm from the University of California, San Diego, CSE department. My advisor is Chang, a leading mathematician and a renowned expert in the CAD field. Yeah. I'm truly honored to present at ISPT 2025. My paper and presentation introduce cell-flex metrics, a method to evaluate how well standard cells for advanced technology can be placed and routed. So yeah, now let's begin. So this is the outline of today's presentation. Introduction, problem statement, contribution, our paper contents, and conclusion and future work. This is the introduction. We continue to follow Moore's law through logic scaling. However, as physical pitch scaling slows down, it becomes increasingly challenging to maintain the same pace of scaling. Moreover, area gains at the cell level do not directly translate into block level area scaling. This is because of three factors. First, limitations in routing resources. Second, increased pin density. Even if the cell area remains the same, the number of pins does not decrease. Uh, this leads to higher pin density. 3. Complexity of the power delivery network. Mm, So, to achieve the expected block level area reduction, we need a systematic methodology and meaningful indicators that link cell design to block design. This is also one of our motivations. We define this as a cell layout flexibility problem and classify it into three key indicators. A. Pin access flexibility. A pin access point does not always guarantee that pin can be promoted to an upper metal layer route. And B. Cell placement flexibility. The power delivery network method can block pin access and constrain cell legalization. And C. Track utilization flexibility. So metal tracks occupied by a cell inside may force detour routing for the connection of other cells. This is our contribution. We propose cell flex metrics to evaluate cell layout flexibility, which includes PAF, PPF, TUF, and we regenerate the cell layout based on cell flex metrics. We consider this as an objective. We can get block area reduction without increasing design violations. And we develop a machine learning model based on Kolmogorov-Arnold network, which is KAN, for DRE prediction. We demonstrate a strong correlation between our cell flex metric and DRBs. Yeah, first metric is cell placement flexibility, which is CPF. Represents the extent to which a cell can be freely assigned within a block. So, mm, by leveraging the periodic nature of the power delivery network we can see in the left figure, we can effectively measure a cell CPF. And we formulate the CPF through the right figure definition. So we incorporate PDN constraint, placement distance, and area penetrance factor for CPF. This is PAF, pin access flexibility. Every routing related metric focuses on pin access points. However, PAF evaluates the number of feasible routing paths scenarios a cell can achieve. So it considers PDN constraint and other design rules. Our approach constructs a pin access tree for each pin in the cell using a breadth first search algorithm and extract feasible routing scenarios from the search tree. This is explained by the figure. So we can get setup routing scenarios from the previous algorithm, and this routing scenario differ from the placement group because PDM method can overlap with pin endpoint and it constrains the number of routing scenarios. So this factor is also considered. And our PA formulation accounts for the number of pins also, because we have to normalize the number of round scenarios by the number of pins. So it ensures that cells with different pin counts maintain comparable flexibility measures. Lastly, this is the track utilization flexibility, which is TUF. TUF includes passing tracks and via availability. Passing tracks refer to unused tracks inside the cell that can be used by the router. The router can penetrate the cell left, right, top, bottom. And via availability helps router to change the routing method routing direction. So this figure illustrates how passing tracks and via availability can help simplify the required routing. To make the news library based on self-select metrics, we incorporate the formulation A for TF and B for CTF into the SMT code. And additionally, we swap the method location in the finalized layout using a search tree algorithm to identify the optimal method arrangement that maximizes PAF. So by applying A, B, and C, we regenerate 41 cells from probe 3.0. This is the table for self-flex comparison between previous library probe 3.0 and our proposed library. We include 20 cells, which is predominantly used in the block experiments. And as you see in this table, the average value of the PAF significantly improved from 1.71 to 3.88. And however, RPA, previous PNFS metric, the value is not that different. However, CPF increased a lot, and TUF average is a little bit similar, but in the bigger cell flip-flop, TUF increased a lot. So, using our proposed library and the probe library, we implemented experiments to determine the smallest possible block area for 5 different RTL cases. Uh, so, we keep DLBs below 200 while implementing the block experiments. The overall block area reduction achieved was 13.2%, aligning with the improvements observed in the flex metric in the previous table. To demonstrate how well self-flex represents placement and routing complexity, we developed a machine learning model to train the correlation between DRV and self-flex metrics. We selected KAN for our machine learning model because KAN allowing for a non-linear transformation and adaptive activation functions. So we think this flexibility enables KAN to effectively capture complex and non-linear relationships in our dataset. We treated routing complexity as heat and applied a distributed heat method to compute the propagated complexity to other G-cells. In our heat formulation, we subtract each feature value from the maximum feature value, establishing an inverse relationship between the feature and complexity. And we selected accuracy and F1 score as our evaluation metrics. And the grid features in the below table include the total pin count and cell area of cells inside each tree cell. This table shows that our feature combination, which incorporates our metrics, achieves better performance compared to grid alone and grid plus the previous pin accessibility metric. So this is the figure of F1 score. We validated our proposed routing scenario-based PAF metric more effectively reflects cell layout quality compared to the existing pin accessibility metric. Furthermore, the results confirm that a trained model incorporating the full set of self-reflect metrics and features enables a more sophisticated and accurate prediction of DRB occurrences. And this is our conclusion. We introduced the self-reflect metrics, PAF, PPF, and CUF, and we integrate self-reflect metrics into cell layer generation, and we achieve 13.2% block area reduction without increasing DRB, and we prove the correlation between self-reflect features and DRB occurrences by developing and machine learning models. So it means this self-reflect metric can be operated as an important indicator for gen layout quality. This is our future work. First, we want to extend the scope of machine learning models. We only tried KAN in this paper, but we want to navigate more machine learning models to train our features. So we want to compare it, and we want to make one more feature that represent inaccessibility, which can be derived from PAS. And I think this feature can be more directly connected to the DRV. And we want to integrate self-rest metrics into cell layer automation. So we are now making some layer synthesis tool to incorporate this. This is all of my presentation, and thank you for listening.